All right, let's continue talking about the application of differentiation. I'm going to turn to concavity and a second derivative test. Concavity refer to concaving upward and concaving downward. So this is a typical case of concaving upward, concaving downward. And we talk about first derivative test, and in this particular section we're going to focus on second derivative test. And it's used to test the extremer. Okay, we will learn how to determine intervals on which a function is concave upward or concave downward. We'll learn how to find any points of infraction of the graph of a function, apply the second derivative test to find relative extremers of a function. Concavity, again, as I mentioned, two types of concavity: concave upward, concave downward. Definition of concavity: let f be a differentiable function on an open interval I. The graph of f is concave upward if f prime is increasing on the interval. Same thing as saying slope of tangent line is increasing. And a concave downward on interval I if f prime is decreasing on the interval, meaning slope of tangent line is decreasing. Let's take a look at how we interpret this, right? Let me show you. This is concave upward. Typical case of concave upward. As you can see, if you draw the tangent line, you start with a very small negative number, then keep getting bigger until we reach 0, right? Have a horizontal tangent here which slope is 0. Then when you move upward, you see that slope become positive, and then it becomes bigger and bigger because the line becomes more steep. Okay, so going from negative, very small negative number, to 0, and gradually move up to very big positive number. So this is increasing, so slope of tangent line is increasing. And for the concave downward case, it's exactly opposite. So meaning you get a graph like this. Then if you look at the slope of tangent line, she's just getting bigger. Start with a positive value, right? Then becomes smaller and smaller, and at the extreme here it becomes 0 with the horizontal tangent. Then it's just getting smaller and smaller. Negative, very negative. Start with positive, very positive, big positive number, to 0 until negative, right? So that's why the slope of tangent line is decreasing here for the concaving downward case. And let's look at concavity in a more deep manner. So the following graphical interpretation of concavity is useful. Let f be differentiable on open interval I. If the graph of f is concave upward on interval I, then the graph of f lies above all of its tangent lines on I. Also, you see all these tangent lines are below the curve itself. Okay, if you look at the value, right, start with the negative value, it becomes positive, becomes bigger positive values. So slope tangent line is increasing in this case. Secondly, let f be differentiable on the open interval I if the graph of f is concave downward on interval I, then the graph of f lies below all of its tangent line on I. So all these tangent line is on top of the curve itself. As you can see, this is positive value because negative become smaller negative value. So you see the slope tangent line is decreasing. They're pretty consistent too. The observation is consistent with the trend of the slope. Okay, so let's take a look at the test for concavity. That be a function whose second derivative exists on the open interval I. If the second derivative of function f of x is greater than 0, for all x in I, then the graph of f concave upward on I. Secondly, if f double prime of x is less than 0, meaning second derivative of x. Same thing as slope of not slope anymore. So this is like the second derivative of f of x is less than 0 for all x in I. And the graph of f is concaving downward. So second derivative is key thing. Second derivative is needed for test of concavity. Alright, let's look at example, see how we determine the concavity. Determine the open intervals on which the graph of f of x equals to 6 over x squared plus 3 is concave upward or downward. If you look at the function, since x squared plus 3 is always greater or equal than 3, so the denominator is never going to be 0. So the domain here, domain of function f of x is going to be from negative infinity to positive infinity. This is very important when we carry out a problem later. But first of all, we need to find out the second derivative in order to test the concavity. So first of all, we got to find the first derivative in order to find the second derivative. And here we're going to use the quotient rule. So numerator is f, denominator is g. When f equals 6, f prime, the derivative of constant is 0, right? G equals to x squared plus 3, and g prime is going to be 2x plus 0, which is just 2x. Now we can apply the quotient rule. The quotient rule, prime g minus fg prime over g squared. So f prime of x equals f prime, which is 0 times g. G is x squared plus 3 minus f, which is 6 times g prime 2x over g squared, so it's x squared plus 3 times c squared. If you simplify these, 0 times anything is 0, so you get negative 12x over x squared plus 3 squared. Okay, that's going to be the first derivative. So again, we're going to apply the quotient rule one more time. F now is negative 12x. F prime is negative 12. G is x squared plus 3 squared. And G prime, we're going to apply the chain rule here. First of all, you apply the power rule. X squared plus 3 reduce the power by 1. And we differentiate inner function. So the inner function is going to be derivative of x squared is 2x. Derivative of 3 is 0. Okay, so we get a 2 times 2x times x squared plus 3. So we get a 4x times x squared plus 3. Okay. Alright, so now we're gonna apply the quotient rule one more time. F double prime of x equals to f prime, which is negative 12 times g x squared plus 3 squared minus f, which is negative 12x times g prime. G prime is 4x times x squared plus 3 over, and g squared is x squared plus 3 square. Okay, so now we gotta simplify this. So we get negative 12 x squared plus 3 square minus plus, right? Minus become plus 48x squared plus 3. Bottom is x squared plus 3 to the 4th. Okay, then we're gonna reduce every single term on top and bottom by x squared plus 3. So now we get negative 12 x squared plus 3 plus 48x squared over x squared plus 3 cube. Then distribute it, combine like terms, we get negative 12x squared minus 36 plus 48x squared over x squared plus 3 to the 3rd. Then it becomes 36x squared minus 36 over x squared plus 3 cubed to the 3rd. So that's the second derivative. Then next we're going to figure out the numbers we're going to test for concavity. So we're setting f double prime of x equals 0. That means 36x squared minus 36 over x squared plus 3 to the 3rd, 0. Use cross multiplication, we end up with 36x squared minus 36 equals 0. Then we solve for x. Factor out 36 x squared minus 1 equals 0. Setting x squared minus 1 equals 0, then x equals plus minus 1. Okay, so now we find out the possible values to test for concavity. Once you have that, then we can start create a table and start testing, right? So we're gonna create a table. So start with test interval. From x infinity to the x value is plus minus 1. So that those two values are going to separate the domain into 3 pieces. 1 to 1, 1 to positive infinity. I'm going to pick test value within each interval. So here we can pick -2, 0, 2. Then we start determining sign of f double prime of x. So f double prime of -2. So f double prime of x equals 36x squared minus 36 over x squared plus 3 to the third. If you look at the equation, the denominator is always going to be positive. So we have 36 times -2 squared minus 36 on top over -2 squared plus 3 to the third. On top we have 144 minus 36 over, and denominator is 7 cubed. 144 minus 36 is 8 over 7 cubed. This is definitely greater than 0, so it's positive. You don't need to figure out the answer. All you need to do is determine the sign. Once you know the sign, then you're ready to go. So the conclusion for this case, this is concave upward. The second one, second interval, at the f double prime of 0, so it becomes 36 times 0 minus 36 over 0 squared plus 3 to the third, so it becomes -36 over 3 cubed. This is definitely less than 0, so it's negative. Negative indicates concave downward. The third interval, 2f double prime of 2 equals 36 times 2 squared minus 36. And 2 squared plus 3 to the third. It becomes 144 minus 36 over 7 cubed. 1/7 cubed. Again, it's greater than 0, so it's positive. That means it's concave upward.
Recording something? Oh, sorry. You have a recording video. It's okay. No worries. Do you have a headphones? Like maybe the ones that using a USB or headphones? Any headphones?
I don't think I have one, Eugene.
No.
Yeah.
Let me ask you.
Maybe, do you want this one? This is
No, I need
no,
something.
oh,
I have
for the
no-
phone, for cell phone.
Yeah, something
Okay.
for the computer, but something that I can just
I see.
hear while people are around. Okay, thank you.
No problem. Okay, so that's pretty much it. So we figured out the concavity for each interval, and the table is the best way to perform the test for concavity. As you can see, this table is a summary of what we just did, and the result actually is consistent with our analysis. So as you can see, from -infinity to -1, this is concaving upward. Okay. Okay, and then from -1 to 1, it's concaving downward. And then from concaving upward to concaving downward, this is the inflection point, right? We're gonna get to that in a second, but that's what happened here. And from 1 to positive infinity, again, it's concaving upward. That's at this point. This is another point of inflection. We're gonna get to that concept in a second, but the graph actually is consistent with our analysis. And now let's take a look at the point of infractions. Point of infraction is where concavity changes. Concavity changes. Meaning change from concaving upward to downward, or concave downward to upward. If the tangent line to the graph exists at such a point where the concavity changes, so this keyword, concavity changes, that point is a point of infraction. Three types of points of infraction are shown in below. So start with the concaving upward, to concaving downward. So we get a point of infraction here. Second case, start with the concaving downward, concaving upward. That's a point of infraction here. Third case, concaving upward, concaving downward, point of infraction in the middle. So three different cases where the concavity changes. And at that point, that's a point of infraction. Let's take a look at the definition of a point of infraction. Let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at this point, c comma f of c, then this point is a point of infraction of the graph of f if the concavity of f changes from upward to downward or downward to upward at a point. Point of infraction theorem about the point of infraction. If c comma f of c is a point of infraction of the graph of f, then either f double prime of c equals 0, or f double prime second derivative does not exist at x equals c, meaning it's undefined. Example 3, finding points of infraction. Determine a point of infraction and discuss the concavity of the graph of f of x equals x to the 4th minus 4x cubed. So in order to figure out the point of infraction, we have to find the second derivative. So in order to find the second derivative, we gotta find the first derivative. So the first derivative, we apply the power rule. So 4 times x, 4 minus 1, minus 4 times 3 times x, 3 minus 1. So end up with 4x cubed minus 12x squared. After finding the first derivative and second derivative, you apply the power rule one more time. So 4 times 3 times x, 3 minus 1, minus 12 times x, 2 minus 1, times 2 minus 1. Remember to put the exponents in front. So 2 goes in front, x, 2 minus 1. So end up with 12x squared minus 24x. And now we set the second derivative equals 0 and solve for x. So set f double prime of x equals 0. That means 12x squared minus 24x equals 0. And if you factor out 12x, then we get x minus 2 equals 0. If say each one of them, each factor equals 0, we get x equals 0, x minus 2 equals 0. X equals 2. 0 and 2 are the points we have to check, right? So now let's create a table. So the test interval first one, let's start with the domain of f of x. Since it's the 4th degree polynomial function, so the domain is all real numbers. It's from negative infinity to positive infinity. So the first interval is 0, 2 will separate the whole domain into 3 subintervals. So the first one is from negative infinity to 0, and 0 to 2, and from 2 to positive infinity. I'm going to pick the value from each interval. First interval we can pick negative 1, second interval 1, third interval we pick 3. Then we determine sign of f double prime of x. So f double prime of x for negative 1. So you get a 12 times negative 1 squared minus 24 times negative 1. It becomes 12 plus 24, which is 36. This is definitely positive. Greater than 0, so positive. Positive tells us it's concaving upward. The second interval, the test value is 1.